Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here begins the essay, Michael Atiyah's Geometry and Physics, delivered as a lecture in 1979, marks a pivotal moment in the burgeoning interaction between two seemingly disparate fields. This essay aims to provide a detailed evaluation of the claims presented within that lecture, dissecting its key arguments and assessing their impact on the subsequent development of mathematical physics. We will proceed systematically through its unfolding narrative, scrutinizing the evidence and conceptual framework at Section 1. The initial bridge gauge fields and instantons. Atiyah begins by establishing a connection between gauge fields, fundamental objects in quantum field theory, and geometric concepts, specifically instantons. He proposes that a profound relationship exists between solutions to classical field equations in Yang-Mills theory and the topology of the underlying space on which these fields are defined. It is asserted that the existence of instanton solutions, self-dual solutions to the Yang-Mills equations, is intimately linked to the non-trivial topology of four-dimensional Euclidean space. The claim centers on the idea that the number of instanton solutions with a given topological charge, often referred to as the instanton number, can be calculated using topological invariance. This topological charge, an integer characterizing the winding of the gauge field at infinity, plays a crucial role. Atiyah highlights the significance of self-duality, a condition that simplifies the Yang-Mills equations and allows for exact solutions. The lecture indicates a route to understanding complex physical phenomena through the lens of pure geometry, suggesting that the properties of space itself dictate the behavior of fundamental forces. This opening gambit, while revolutionary, depends heavily on mathematical rigor to properly define the topological invariants involved and demonstrate the existence and completeness of the instanton solutions. Section 2. The index theorem, a powerful unification. Atiyah introduces the Atiyah-Singer index theorem as a cornerstone in the unification of geometry and physics. The theorem, a deep result in differential geometry and topology, relates the analytic index of an elliptic differential operator to its topological index. The analytic index, defined in terms of the dimensions of the kernel and cokernel of the operator, reflects the number of solutions for a certain differential equation. The topological index, on the other hand, is calculated from topological invariants associated with the operator and the manifold on which it acts. The index theorem asserts, therefore, a surprising equality between these two seemingly unrelated quantities. Atiyah emphasizes its broad applicability, stating the theorem can be used to calculate the number of zero modes of certain operators arising in quantum field theory, such as the Dirac operator, in the presence of a gauge field. The presence of zero modes, solutions to the Dirac equation with zero eigenvalue, is directly tied to the topological charge of the gauge field, thus connecting quantum phenomena to topological properties. The potency of this connection stems from its precision. It provides an exact, calculable relationship between physical quantities and topological invariants, lending itself to powerful theoretical predictions. However, he also acknowledges the theorem's complexity, underscoring the need for sophisticated mathematical tools to fully grasp its implications and implement it effectively. Section 3. Supersymmetry and the Dirac operator. Atiyah explores the role of supersymmetry, a symmetry that relates bosons and fermions. In simplifying and understanding the index theorem, he suggests that supersymmetric theories offer a natural framework for interpreting the index theorem in terms of cancellation between bosonic and fermionic degrees of freedom. In a supersymmetric theory, for every bosonic particle, there exists a corresponding fermionic partner, and vice versa. This symmetry leads to cancellations in certain calculations, simplifying the analysis of quantum field theory. Atiyah argues that the Dirac operator, which plays a central role in the index theorem, has a natural interpretation within the context of supersymmetry. Specifically, it can be viewed as a supersymmetric operator whose index counts the difference between the number of bosonic and fermionic zero modes. This supersymmetric perspective provides a deeper understanding of the index theorem and its connection to quantum field theory. The beauty of this interpretation lies in its elegance. It demonstrates how a seemingly abstract mathematical theorem can be elegantly realized within the framework of a physical theory. It hints at a deeper underlying structure, a harmony between geometry and physics revealed through the lens of supersymmetry. Section 4, Twistor theory, a novel geometric approach. He introduces twistor theory, developed primarily by Roger Penrose, as a radical approach to understanding spacetime and physical fields. Twistor theory proposes that spacetime is not the fundamental object, but rather an emergent concept arising from a more fundamental geometric structure called twistor space. Twistor space is a complex space whose points correspond to null lines in spacetime. By representing spacetime points as geometric objects in twistor space, twistor theory reformulates physical laws in terms of complex geometry. Atiyah suggests that twistor theory provides a powerful tool for solving certain differential equations arising in physics, particularly those related to self-dual gauge fields and Einstein's equations. He argues that twistor theory simplifies these equations by transforming them into algebraic equations in twistor space, which are often easier to solve. Twistor theory provides a unique and potentially revolutionary perspective on the nature of spacetime and physical fields, but it requires a significant shift in perspective and a mastery of complex geometry. The true power and scope of twistor theory remains an area of active research, with ongoing efforts to apply it to a wider range of physical problems. While challenging, the potential rewards are immense, offering the possibility of a deeper understanding of the fundamental laws of nature. Section 5, the Yang-Mills equations and moduli spaces. Atiyah delves into the geometry of moduli spaces of solutions to the Yang-Mills equations. He posits that understanding the structure of these moduli spaces, the spaces that parameterize the solutions to the Yang-Mills equations, is crucial for understanding the quantum behavior of gauge fields. Each point in the moduli space corresponds to a particular solution of the Yang-Mills equations. The geometry of the moduli space, its dimension, topology, and singularities encodes information about the number and properties of these solutions. Atiyah emphasizes the difficulty in constructing and analyzing these moduli spaces, highlighting the need for sophisticated mathematical techniques from algebraic geometry and topology. He suggests that the study of these moduli spaces will provide insights into the non-perturbative aspects of quantum field theory, phenomena that are beyond the reach of traditional perturbative methods. This approach advocates for delving into the deep waters of geometric abstraction to extract physical insight. The challenge lies in translating the geometric properties of moduli spaces into concrete physical predictions, a task that requires bridging the gap between abstract mathematics and experimental observation. Section 6. Instantons and four-manifold topology. Atiyah explores the deep connection between instantons and the topology of four-dimensional manifolds. He suggests that the existence and properties of instanton solutions to the Yang-Mills equations can be used to probe the topology of the underlying four-manifold. This connection arises from the fact that the instanton number, a topological invariant characterizing the instanton solution, is related to topological invariants of the manifold itself. The lecture posits that by studying the moduli spaces of instantons on a given four-manifold, one can gain information about its topology. This approach has led to profound results in the study of four-manifolds, including the discovery of exotic smooth structures on Euclidean space. The significance of this connection lies in its ability to translate difficult topological problems into more manageable problems in differential geometry and analysis. By studying the solutions of differential equations on a manifold, Mathematicians can gain insights into its global topological properties. This approach exemplifies the power of mathematical physics to solve problems in pure mathematics. Section 7 Monopoles and 3 Manifold Topology. He draws a parallel between instantons in 4 dimensions and magnetic monopoles in 3 dimensions, emphasizing that similar geometric techniques can be applied to study both magnetic monopoles, hypothetical particles with isolated magnetic charge, are solutions to certain gauge field equations in 3 dimensions. Atiyah argues that the study of monopoles, like that of instantons, is intimately related to the topology of the underlying space. He suggests that the moduli spaces of monopoles on the 3-manifold can be used to probe its topological properties. This analogy extends a successful approach used to study instantons and 4-manifolds to the realm of monopoles and 3-manifolds. By applying similar geometric techniques, mathematicians can gain insights into the topology of 3-dimensional spaces. The extension of these ideas to lower dimensions demonstrates the generality and robustness of the underlying geometric framework. It highlights a potential for applying these techniques to a wide range of problems in both mathematics and physics. Section 8 Quantum Field Theory and Geometry. A unified view. Atiyah contemplates the possibility of a fully unified view of quantum field theory and geometry, positing that the two are deeply intertwined aspects of a single underlying reality. He suggests that the tools and concepts of geometry provide a powerful framework for understanding the structure and behavior of quantum fields. Conversely, he argues that quantum field theory can provide insights into the nature of geometry itself, leading to new and unexpected mathematical discoveries. He envisions a future where the boundaries between mathematics and physics become increasingly blurred, with researchers freely moving back and forth between the two disciplines, leveraging the tools and insights of each to advance our understanding of the universe. This vision represents the culmination of the themes explored throughout the lecture. It envisions a future where mathematics and physics are no longer seen as separate disciplines, but rather as complementary aspects of a unified intellectual pursuit. The realization of this vision requires a deep understanding of both fields, as well as a willingness to embrace new and unconventional Section 9 Concluding Remarks. Enduring Impact and Future Directions. In his concluding remarks, Atiyah reflects on the impact of the connections between geometry and physics and outlines potential directions for future research. He emphasizes that the interplay between these two fields has led to profound advances in both mathematics and physics. The discovery of instantons, the development of twistor theory, and the application of the index theorem to quantum field theory are just a few examples of the fruits of this collaboration. He suggests that future research should focus on exploring the deeper connections between geometry and quantum field theory, with particular emphasis on understanding the non-perturbative aspects of quantum field theory and the nature of spacetime at the Planck scale. This concluding statement underscores the ongoing nature of this intellectual journey. It calls for continued exploration, for the pursuit of new ideas and the development of new tools to probe the mysteries of the universe. The path forward requires a spirit of collaboration, a willingness to embrace new perspectives, and a deep commitment to both mathematical rigor and physical insight. In conclusion, Atiyah's 1979 lecture Geometry and Physics presents a compelling vision of the deep and fruitful interplay between these two fundamental disciplines. Through a systematic examination of gauge fields, the index theorem, supersymmetry, twistor theory, and moduli spaces, the lecture demonstrates how geometric concepts can be used to illuminate the structure and behavior of quantum fields. Conversely, it highlights how quantum field theory can provide insights into the nature of geometry itself. While the lecture makes bold claims about the power and potential of this unified approach, it also acknowledges the challenges and complexities involved. The enduring significance of Atiyah's work lies in its ability To inspire and guide researchers at the intersection of mathematics and physics, it has set the stage for decades of fruitful collaboration, leading to profound advances in our understanding of the universe. The claims within the lecture, while ambitious, have served as a powerful catalyst for intellectual exploration, pushing the boundaries of both mathematics and physics and paving the way for new and exciting discoveries. The lecture's vision, while still not fully realised, remains a potent force driving research in mathematical physics. It is a testament to the power of interdisciplinary thinking and the enduring quest to uncover the fundamental laws of nature.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.